So we left off here last time talking about electron configurations and orbital diagrams. These are our two ways of representing where electrons are inside of the atom. Now in each of these we're going to be given some information, or we are giving some information about the quantum numbers that describe each of the electrons. For orbital diagrams, we're going to be giving all four numbers. So there's enough information in an orbital diagram that you can work out the four quantum numbers for any electron in the diagram. Now, in an electron configuration, you really only give two, really, at the most. You're only getting two that you don't even really know the exact orbital that the electron is sitting in. But truthfully, most of the time, we don't really care whether an electron is sitting in the px, py, or pz orbital. It doesn't really matter to us. So most of the time, we're going to be perfectly fine with just using these electron configurations. So when we're putting electrons into either of these, our guiding principle is going to be that we are going to start putting electrons into the lowest energy orbitals, and then just continue to put electrons in until we run out of electrons, starting with the low energy and working our way up. Which then begs the question, how do we know what the proper order is? How do we know what's low energy and what's higher energy? Well, this graph shows us that the lowest energy orbitals are the 1s, and this should make sense because it's the smallest principal number, and it's the only orbital in that smallest principal shell. It gets more complicated, though, as we start to go up. Because as you can see here, yes, the second principal shell, is lower than anything in the 3. But once we get into the third principal shell, the S versus P versus D subshells, they start to spread out, mainly because of the complexity of the shape of the orbitals. Because of the shapes of the orbitals, the D have a higher energy than the S. And the P has a higher energy than the S as well. And so the D, that shape, gives it enough extra energy. It's at a high enough energy that actually is higher than the 4s. So the 3d is at a higher energy than the 4s. So we can't just say fill all the 1s, fill all the 2s, fill all the 3s, fill all the 4s, and you're fine. Because of this staggering, if you will, of the energies, because of the different shapes of orbitals, we have to actually know the correct order for these things. We can't just go 1, 2, 3, 4. So specifically here, the order that we're going to go in is we're going to go from the 1s, the next lowest energy is the 2s, and then the 2p, and then the 3s, and then the 3p, and then the 4s, and then the 3d, 4p, 5s, 4d, and so on. And if you're thinking, oh my gosh, I don't want to have to memorize this, I have good news. You don't need to. You just need to know how to read this thing. So this is our handy-dandy guide for determining the correct order in which to fill subshells. Now, I know this kind of looks like a mess at first glance, but what this is doing is we're started here with the first principal shell, and each of these subsequent rows is just the next principal shell. And then inside of each of these rows, we've just listed, one after the other, each of the individual subshells. So the S, P, D, and then F, and we don't go above F. Technically, there is a G, and an H, and an I. Technically, it goes beyond that, but we're never going to worry about those. To use this, what we're going to do is we're just going to start in the top right corner. Well, technically this is the top left, but the highest column here and in the top right corner of this section, and just draw a diagonal line down and to the left. And we're going to do that with each subsequent row. As you can see here, we're just drawing a diagonal line down and to the left. And when we get to the end, where we're not running into any more subshells, we're just going to work our way back up to that same position on the next one, and work our way down, and then back up, and down, and back up, and down. And when we do this, the order in which we intersect these subshells is actually this order, the correct order of the energies of these subshells. And so we don't have to memorize the order. We are just going to use this as our guide and make sure that we're following the correct order here. So we have 1s, and then 2s, 2p, 3s, 3p, 4s, 3d, and so on. I'm not going to read through that whole thing. But this will always give you the correct order. And I don't think we'll ever go above 6d, but if for some reason you just feel like doing some extra chemistry and you want to go above 6d, it would still continue on the same thing here. This would be 7p, 7d, this would be 6f, 7f, and you would have 8s down here as well. You would just fill out the table the rest of the way, and it would still give you the correct order. All right, so when we're doing these, when we're filling in these electron configurations, we have a couple other rules that we need to follow. So the first one we've already mentioned here, we always fill from low energy to high energy. The universe is lazy. It's not going to put electrons into a high energy orbital unless you do something to make the electrons go there. The electrons are going to be at the lowest energy they can. This is what we call the ground state, by the way. All of the electron configurations and orbitals, orbital diagrams we're going to write are going to be the ground state, the lowest energy possible. The next one here, an orbital can only contain 2 electrons, and those 2 electrons have to have opposite spin. This is what we call the Pauli exclusion principle. So when we're drawing orbital diagrams, we're going to represent the orbitals as boxes. We can never have 2 electrons with spin up or 2 electrons with spin down. Those are not allowed. Every orbital can only hold 2 electrons, and they have to be spinning in opposite directions. So then the last one here, when orbitals of identical energy are available, put a single electron in each of the identical orbitals before pairing them, and all the single electron in orbitals should have parallel spins. So if, for example, we're putting electrons into the 2p, so the 2p subshell has 3 orbitals. If you remember, all the p subshells have 3 orbitals, and we have 3 electrons to put into the 2p. We're not going to do 1, 2, and 3. That's incorrect. Hund's rule tells us that we need to do 1, 2, 3. Electrons like their space. They don't want to be paired up unless they have to be. And so if you can give the electrons their own individual orbitals inside of the subshell, you should do that. And not only that, they like to have the same spin. So you should put them all either spin up or spin down. It doesn't actually matter which direction, as long as they're all the same. I usually put them as spin up just because I'm a positive person, I guess. So this is what those are going to look like. So here we have the electron configurations and the orbital diagrams of all the elements from lithium through neon, so elements 3 through 10. And as you can see here with lithium, we only have 3 electrons. So for the electron configuration, we start with 1s. We put the number of electrons up here as the exponent. So this is telling us that in the 1s subshell, there are 2 electrons. That is the most that subshell can hold. And so then we move on to the next subshell, which was the 2s. It can hold up to 2, but we only have 1 left, because we only had 3 to start with. And so this is 2s1. So then in an orbital diagram, it would look like this, where we would have a box again for every orbital, and you do have to have them labeled. We can't just draw random boxes on the page. They do have to be labeled 1s, 2s, 2p, and so on. And you represent each of the electrons as a one-sided arrow. So we have one spin up, one spin down, and then another one spin up in the 2s. If we skip down here to oxygen, so oxygen has 8 electrons. Once again, we're just going to start with the lowest energy subshell, which is the 1s, and just put electrons in until we run out. So the s can hold 2, so we have 1s2. The next highest energy is 2s. That can also hold 2, so now that one's full. The next energy up is the 2p. It can hold up to 6, but we only have 4 electrons left. And so it's 2p4. It only has 4 electrons in it. And so in an orbital diagram, once again, one box for the s subshells, because they only have 1 orbital. The p subshell has 3, so we're going to have 3 boxes, one for each of the orbitals. And when we're putting those 4 electrons in, we put them in singly first, so we had 1, 2, 3, and then we had 1 more, and so we just went back to that first one and paired it up. And they get completely paired by the time you get down to neon, because you have 6 more electrons, well, not 6 more, but 2 more, which gives you 6 in the 2p. All right. So the really, really good news about these electron configurations and orbital diagrams is that these do not change in any way from one element to the next, with the exception of the number of electrons. That is the only thing that changes from one orbital to the next, or from one element to the next. The order in which you fill them, the rules about how you fill them, that does not change. Doesn't matter if you're looking at metals or nonmetals or transition metals or radioactive elements, doesn't matter. Everything gets filled exactly the same way. The rules are always the same. The order is always the same. The only thing that changes is the number of electrons that you put into the configuration or the diagram. That's the only thing that changes. So let's do a few examples here where it's not already worked out on the screen. So we have magnesium, sulfur, and gallium. So we're going to write the electron configurations of each, and let me see, do I have us do, yeah. Why don't we go ahead and do a few of these with the orbital diagrams as well. So, actually let's just do all of them with both electron configuration and orbital diagram. Why not? So the first one there, magnesium. Anytime I'm asked to find or to write an electron configuration or an orbital diagram, the very first thing that I do, and the very first thing that you should do, is figure out how many electrons do I have. Well, if you go to the periodic table, you will find that magnesium has 12 electrons. It's element number 12. It's going to have the same number of electrons as protons, so it has 12 electrons. So what I'm going to do is I'm just going to start with the lowest energy, which is the 1s, and just fill in electrons until I run out. So 1s is first. It can hold 2 electrons. 2s is next. It can hold 2 electrons. 2p comes after that. How many electrons can p orbitals hold? Yep, 6. Can hold 6 electrons. They have 3 orbitals, 2 electrons each. So that's 6. So far I've put in 10 electrons. The next highest or lowest, depending on which direction you're looking from, orbital or subshell is the 3s. And it can hold 2 electrons, which is all the electrons I have left, because I only have 12 electrons. So that is the electron configuration for magnesium. Let's do sulfur. So sulfur, if I look it up on the periodic table, has 16 electrons. So I'm going to do the exact same thing that I did for magnesium. Start with a 1s and work my way up. 1s can hold 2, 2s can hold 2, 2p can hold 6. That's 10 electrons so far. I have 6 more to go. 3s can hold 2. What's after the 3s? If you can't remember, you can go back to here. So I did 2p, I did 3s, follow this back up, 3p is next. So I have 3p, and how many do I get to put in there? It can hold a maximum of 6, but do I have 6? I do not. I do not have 6, because I'm up to 12 at this point, and I only have 16 to give. So I only have 4 to put in there, which is perfectly fine. It doesn't have to hold 6. It could hold 0. It could be completely empty. It's just 6 is the maximum it can hold. So that is the electron configuration for sulfur. So then the last one here on this slide anyway, gallium. If I look at the periodic table, gallium has 31 electrons. It's a bit bigger. That's okay. I treat everything exactly the same. So I'm just going to start here with 1s. It's going to have 2, 2s2, 2p6, 3s2. Now I'm at the point where I finished with sulfur there. The p can hold 6, and right now I have 18 electrons in my configuration. So I still have a decent bit more to go. So what's after the 3p? It's very tempting to say 3d, but 3d is not next. 4s, remember this is where they start to get out of order. Up to this point, everything was just in order based on the principal quantum number. But now the 4s gets in front of the 3d, and from this point forward, they're all kind of mixed up. So we really need to reference this when we're doing these. So 4s is next, and then 3d. So the 4s, all s subshells can hold 2 electrons. So there's now 20 electrons in my configuration. 3d was next. How many electrons can the d orbital hold? It can hold 10. It has 5 orbitals. Each of them can hold 2 electrons, so we have 10. So I am now up to 30 electrons. I have 1 left that I need to put in. What's after 3d? Well, again, if you can't remember, just go right back here. 3d, 4p. And I only have 1 electron left, so it gets 1. And that's it. That's all there is for these electron configurations. Usually, when I'm teaching this in class, and I'm talking about quantum numbers and throwing around angular momentum and the magnetic spin numbers and all this, students are like, what the heck is going on? And then when I actually explain the process for writing these out, the usual response is, oh, well, that's not that bad. So understanding what's going on is actually much more difficult than actually doing the process of writing out these electron configurations. As long as you know the proper order and you can count, it's pretty straightforward. The only tricky parts come in when you forget the rules. So maybe you put things in with incorrect spins or something like that. Let's go ahead and do some orbital diagrams here real quickly. So for magnesium, we're just going to write this out, but with the actual boxes to represent the individual orbitals. This is 2p, and then we have 3s. Sorry for my poor box drawing skills. But for each of these, we're just going to have an arrow to represent each of the electrons. So the 2p is completely full, and the 3s is also full. So that is what the orbital diagram would look like for magnesium. For sulfur, it's going to look very similar. We're just going to go a little bit farther. So we're going to have our 1s, 2s, there's our 2p, 3s, go ahead and write those in there, and then we're going to have 3p. And so if we just write in our electrons here, we have 2 in each of the s subshells. The 2p is completely full, so we're going to put 2 electrons in each of those. The 3s is completely full. The 3p is not full. It has 4 electrons in it. So what I'm going to do is I'm going to put them in singly first with parallel spins, so all with the same spin, and then I'm going to pair it up with that last one. And technically speaking, you don't have to pair up the first one. You could do the middle one or the last one. The electron doesn't actually care. It's just essentially by convention. Everyone always goes from left to right. But it's not technically wrong if you do the middle one. So that is sulfur. I'm not actually sure I have space to do gallium. Let me erase the sulfur, I guess. So if you're still looking at the sulfur there, go ahead and pause the video to take a good look at that, because I'm going to erase it so I can do the gallium. Get rid of those. Actually, I'll just erase the magnesium too, so I have plenty of space. So then the gallium, which has 31 electrons, it's going to take up more than one row here just because it's bigger. So we have the 1s, the 2s, 2p, 3s, 3p, 4s is after that. The 3d has 5 orbitals. And then we have the 4p. And so to write its orbital diagram, we're just going to fill everything up until we reach the 4p. Because every one of these is full. Remembering to fill them in singly first, and then pair them up. I know it seems kind of unnecessary since I know that it's completely full, but when you're writing these out later and you don't know if it's completely full, so you haven't written out the configuration beforehand, it's good practice to go ahead and write them in singly first, even at this point. So then the 4p, we just have 1 electron, and so again, it wouldn't be technically wrong if you were to put it in the middle one or in the third one here. It's again just by convention, everyone just goes left to right. These orbitals are what we call degenerate, which is kind of a sciencey way of saying they all are exactly the same. They all have exactly the same energy, so it doesn't actually matter which one you put it in. Just by convention, everyone starts with the left one and goes to the right. All right, one last thing here before I finish up this long video. let's go ahead and write the orbital diagram for silicon, but I want you to do it. So go ahead and pause the video now and write the orbital diagram for silicon. I would say try to do it without writing the electron configuration first, just to get a feel for writing the orbital diagram by itself. So go ahead and try that now. All right, so silicon has 14 electrons, which means that I'm going to need at least a few of these subshells. The way that I normally write orbital diagrams, if I don't know where the configuration is going to stop, is I just go ahead and write in a bunch of these, and then whenever I run out of electrons, I run out of electrons. And if I have extra ones written at the end, who cares? They're still there. They exist. They're just empty. So we'll start with these. So I have 14 electrons to put in, so I'm just going to start with 1s and fill them in until I run out. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. If you, when you did this, did 13, 14, that is incorrect. Again, remember Hund's rule. Put them in singly first with parallel spins. Give them their own orbitals if you can. Electrons like their space. All right, we're going to call it there for this video. In the next one, we're going to talk about some classifications of electrons inside of the atom, specifically valence electrons versus what we call core electrons. So I'll talk to you in the next one.